Went out for a minute at Wi-Fi troubles.
Uh, Namuye is in transit. Tinega.
Can hear you. Kwa sawa.
Just a moment. I share my screen. Okay. Can you be able to see my screen? Can you be able to see my screen?
Yes. Yes.
Okay.
Sure.
So today, let's. Does this thing have something? File preference. So this is Openrocket. So you need to download it. So I had shared the link on where to download it. Then I had shared some materials. So we'll just look at 3 designs for today so that we can be able to familiarize ourselves with Openrocket. Can you be able to see my screen clearly?
Yes, it's clear.
Yes.
Okay, so we'll start with the model rocket in Openrocket. Uh, let's see. I cannot. Let's change it to white. Seeing where is it? I cannot be able to change it, so probably I'll have to check with just with the color. But so in this file, this is just an example. You go to here, you open an example, a simple model rocket. So in this model rocket, you can see we have a nose cone and a body tube. Then the
Rodney,
yes,
we can't see whatever you're clicking. We are only seeing
yes, I
our
was trying
dashboard.
to change the color, but I cannot be able to change it. So I don't know what might be the issue.
As in, we can only see the Discord screen. We can't
Ah,
see you opening
okay,
any files. Yeah.
okay. Just a moment. Share. What about now?
Yes, it's clear now.
Can you be able to see this rocket?
Yeah. Yes, yes, yes.
Okay. Sorry for that. So you go here, open an example. This is a simple example. I hope we are still in the same screen. So in this example, you have a nose cone and a body tube. So in the nose cone, you know what a nose cone is. Then we have the body tube. The body tube will now contain the different things. So in the body tube, first thing is the fins. So these are the fins. You can be able to view them. Also, we can be able to change the to change it to say 3D. I think it's a bug. You can be able to see it when we rotate it. Then there is an inner body tube. This is where we attach the engine. So there is an inner body tube, then there is an engine block. The engine block is to prevent the motor from going to this side. So it prevents the motor from going inside. Then these two centerings are for holding the motor into place. Then we have a shock cord, so and a parachute and a warding. Okay, so the shock cord is an elastic material that is used to to hold the parachute to the rocket. So when it flies and it ejects the parachute, you expect it to go down first, then it will absorb the force so that before it will expand the parachute. Then this wording is used to prevent. Yes.
Shitibu pole 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 pole.
Okay. So this wording is used to prevent. It's a fireproof, so it's used to prevent fire on this other side of the rocket. Then there is a launch lug. A launch lug is usually a slot that is used to direct the rocket on the launch pad. This is what Dr. Oke was saying about where you need it to be smooth so that it can be able to reduce friction. So first, let me close. Let me open. Can you see my screen still? I want to open an N2 rocket. Are you able to see N2 rocket? Just a
No,
moment.
no.
How do I share my entire screen? Okay, go live. So this is the N2 rocket. As you can now be able to see it.
Yes.
So in this N2 rocket, this is a little bit complex, but it follows the same paradigm. We have a nose cone and we have a body tube. So in the nose cone, there is usually no material, but for N1, we had a parachute on the nose cone. So here currently, you don't have a material. So in few key parameters you need to consider when designing the nose cone is this shoulder. So this shoulder is used to attach the nose cone to the body tube. So as you can see, you're able to design the length, then you can be able to change the cone shape. So for instance, we can pick a conical shape, an ogive, and power series or parabolic. Then you can be able to change the length, so you can be able to tune it to your certain needs. So you can also be able to change the base diameter, but now the base diameter you don't need to change it because the base diameter is also for the body tube. Then you have to check also the wall thickness. Is it filled or not filled inside the whole space inside? Then you have to also check the material. So if you don't find your material here, you can put a custom material. Let's say something like Nakuja material. Then you specify its density, then add to material database, then okay. So you can be able to see the material. But the material we are working with, PLA, I think it was initially here. I'd seen it somewhere. Okay, no problem. Then this is a surface finish. So most of the times we don't get a smooth polished surface, we get a rough surface. Then when this is now the shoulder, so you can increase the shoulder diameter, but we don't want to increase the diameter. What we want to increase is probably the length, or is it end capped or not. Then you can be able to override certain things when you have been able to test it. For instance, you have been able to test its coefficient of drag, you can be able to override it here. Or you've been able to measure its mass, you can be able to override here and say probably it's 50 grams. So it will show you something here like a weight. Then you can close it. Then the next thing is the body tube. So the body tube, you need to specify the length and the diameter and also the thickness. Then you need to specify the material. For N2 it was fiberglass. Then you can specify, you have to specify that this component is motor mounted because we added the motor inside here. Then you can be able to, you can I think you've seen Saturn 5 or some of the rockets that have a motor overhang where the motor is not exposed outside of the rocket. So you can be able to change the motor overhang here. Then you can be able to specify the ignition. So at launch you can be able to say, let's say 2 seconds after launch. Also this is for the motor. Then you can be able also to override certain properties. On the materials, you can pick here a material. So these are specified. If you don't find here in specified, it becomes custom because this is a custom material. So the first thing is the parachute. The parachute you need to design is the not radial position, is the diameter of the canopy. So, and also the material of the canopy. So a key thing is the coefficient of drag. This will be used later on. This material, this diameter of the canopy, you will be able to see it will be able to increase or decrease our deceleration speed. Then these are the shroud lines I was telling you. So the shroud lines attach to the shock cord. Then the shock cord attaches to the body tube. The shroud lines are not elastic, but the shock cords are elastic. So you attach first to the shroud lines, then to the shock cord. So currently in our configuration we usually have 6 or 8 shroud lines of 30 centimeters each. This is just the uzi used by fundis, fundi wa kiatu. Then we have one shock cord to be able to hold the parachute to the body. Then you can be able to specify its placement. So when I try and move it, you need to specify its length. As you can see, if I increase the length, I can be able to increase its size here down. Also you can be able to specify something where it's placed or its offset. As you can see it's moving. Also we can be able to see the diameter is packed. Then as you have seen, we will be doing dual deployment. So one parachute will be ejected at apogee. You say it's at apogee. Then the other parachute will be ejected at a specific altitude during descent. Let's say 100 meters above the ground. So when it has gone up during descent, when it reaches 100 meters, it will be able to eject. So we can leave it at 100. Then you can talk about the radial position and also the overriding. These we had talked about them. Yes. The next thing is the shock cord. I've talked about the shock cord is the length and the material. So it needs to be an elastic cord, so you can be able to see different materials here. You can be able also to, if you don't find your material, you can be able to create one custom material here. Then what are the shock cord length and packed length or diameter, and also its position. So its position you specify here. So as you can see, you can be able to specify it using this one. Then the next thing is the parachute block. The parachute block is similar to the engine block, but this is to hold so there will be an explosion here, a small explosion. So it's to hold this explosion from going to this side to this side. Also these blocks can be used to separate. So this is just a small block placed inside here to separate between different subsections. So as you can see, we'll have an explosion block. So the explosion will be here. Then the parachute block will be holding the parachute up. So when there is an explosion, it will push this block up and it will remove the parachute. Then this one will be fixed to the rocket. So this one is a flight control block which is used to separate the flight control system and the avionics system. So this is the avionics system. First, the flight control system. The flight control was a rotating mass called a reaction wheel. So this is why we specified using a mass. Then the avionics, it's a camera, it's a flight computer, but you can change the mass type. So it can be able be deployment charge, tracker, payload, battery, recovery hardware, or mass component. So we have the camera, we have the antennas, we have the flight computers, we also have the camera. So in our case, the cameras were facing outside, so we decided to have them as launch lugs. So if I rotate this rocket, you can be able to see two launch lugs and two cameras. This one is this is an antenna, then this is a camera, then this is a launch lug. So this is the launch lug that will be used for launching, and the cameras and antennas are used for tracking and for the avionics system. Then we definitely have the batteries down, then the altimeter block. So this one is to prevent the avionics computer from falling the other side. Then we talked about the launch lug, and you also have the center. We'll finish on the fins. There is the center rings. As you can see, there are two center rings. So there is one here, and the other one is here. Then there is the trapezoidal fin. So you can play around with the fins. So there are different fins. General, you can be able to change it to 4, 5, 6, 7, 8. Or you can be able to even have 3, 2. Then you can be able to change the rotation of the fins, how they are rotated. Also the cant angle. I'll show you a moment what I mean by the root code is this one. This is the tip code, then this is the height, then this is the sweep length, and this is the sweep angle. So you can be able to design different fins, so you can actually even calculate it. Where is it? You can just a moment. Okay. Yeah, okay. So where was I? Fins. So yes, this is the shape I was telling you. So you can be able to even design it here. So you can be able to change it. You see it's reflecting there. You can be able to change it. You can be able to reduce this if you want something like this. Or we have, this is depending on the aerodynamics of the fins. So this is just a section of the fins. This is how you can be able to design it. Then we have the appearance and some comments for why you did some things, this and this, or why you did them like that. Then the next thing is motor configuration. You'll be able to learn this, but let me just I don't have the Nakuja. I have not loaded the Nakuja motors here, but let me just limit it to sorry, let me find a new rocket here. We try and simulate it. I want the motor diameter to be around 38 to 60. Then I want the length to be it was around 150 to 300. So I can be able to pick here a motor. So the motors are, can you be able to see this screen where I'm selecting the motor? You cannot be able to see it. So change windows. You can be able to see it right now. So what I was saying is I had picked it diameter from 38 to 54, then from 50 millimeters to 30 centimeters. Then one thing you need to check is the naming convention. So from A, B, C, D, E, F, the more we are going up is the how we're increasing the impulse. So if I want a higher impulse motor, it would be a J something. So you can pick a J99. Then we can be able to actually see its thrust curve. So you can be able to see this thrust curve, and you can be able to see it had an average, a maximum thrust of 144 newtons. I think this is a little bit low. Let me pick this one. So this one is able to have an average thrust of 1300 newtons, and it had a max thrust of 14. So this is a big motor. We'll try and simulate it with it. So I've added it. Let me shift my window. Now you can be able to see it. Please confirm.
Yes.
Okay, so we've loaded the motor. Then you can do a simulation. So we'll run simulations. Unable to define motor. Let's delete simulations. Then we add a new simulation. We put the motor we had chosen. So we specify the speed. So when you're on the launch site, you'll be able to specify these speeds, stabilize intensity, temperature. Currently we just leave them to the default values. Then we do a simulation and plot. So we plot and we close this. As you can see here, we now have a new simulation. In this simulation, it says you have an apogee of 1513 and a velocity of, it gives us things. So I'll want to show you a flight profile. Change window. Just a moment, I plot it so I can be able to click it and plot the vertical motion. Okay, then let me show you. So I think you cannot be able to see the screen, but you can be able to see that we have successfully run the simulation, and we found an apogee of 1542 and velocity speed of 28 meters, time to apogee 19 minutes, flight time is around 350 seconds. So you can be able to, if you click here plot and export, you can be able to export to different things. So this is the view, and this is what else have we not talked about? I think we've covered a lot. Yes. Any questions up to there? Any questions?